Hi, I'm Dilara Abde from the Weierstrass Institute in Berlin. Thank you to the organizers of the Newsort for the opportunity to present parts of my research. I want to talk about volume exclusion effects in perovskite charge transport modeling. The outline of this presentation is clear. First, we're going to talk about the charge transport model, then about this volume exclusion effects, and lastly, we will discuss the output of some numerical simulations. The results presented here are a joint work with Nicolas Coutier and Patrizio Farrell. So arguably only a few materials have gained such interest within photovoltaics as perovskites. For example, perovskite silicon tandem solar cells have become more efficient than usual single junction silicon cells, and further efficiency gains are likely. Unfortunately, about the exact physical operation mechanisms, still we lack some knowledge, and for the commercialization, a couple of challenges need to be overcome, especially the fast degradation of such devices. So adequate models and simulation tools are needed to understand the device physics better. These two non-scientific articles give a comprehensive introduction into perovskites. But before continuing, what are actually perovskites? So perovskites form a class of crystalline solids with two cations and an anion. The structure of this mineral here is equivalent to the one of a general perovskite material. We see here an idealized unit cell. In reality, crystal defects occur that dynamically appear and reappear. They leave void spaces within the perovskite crystal structure called vacancies, which can be occupied by the ions. This permanently changing crystalline structure affects the electric charge carriers. Thus, researchers agreed on the fact that besides the movement of electrons and holes, we have additional ion migration, which plays a major role. So for formulating now an adequate model, which additionally incorporates this phenomenon, we use a drift-diffusion approach. Taking a three-layer architecture into account where the perovskite is sandwiched between transport layers, we have electrons and holes moving through the whole device, satisfying mass balances which are coupled to the Poisson equation for the electric potential. The movement of electrons and holes can be described by this current density with a diffusion part here and a drift part here. The diffusion coefficient and the mobility can be related via the generalized Einstein relation, where this function f is called statistics function and connects the charge carrier density with its quasi-Fermi potential and the electric potential. This relation is also called state equation. In the simplest case, this function f is equal to an exponential, resulting in a Boltzmann regime, but in general is an integral equation corresponding to Fermi-Dirac or Gauss-Fermi. Now, as mentioned before, we have additional anion vacancies within the perovskite layer, also satisfying mass balances without the right-hand side. To formulate now proper current density descriptions, we have to talk about this so-called volume exclusion effects. We will use synonymously the wording volume exclusion, steric effect, and the limitation of ion depletion. The aim of the inclusion of these effects is clear. We want to take the finite size of ions for the migration through a crystal lattice into account by extending the model thermodynamically consistent. This means that we want to limit the ion concentration to guarantee that the crystal structure will not be destroyed. Let us consider this figure here, where we have the vacancy density in green and the ion density in red, which sum up to the ideal ion density within a crystal. Here within the red area, we are portraying the densities for an ideal unit cell, meaning the vacancy density is 0 and the ideal ion density is reached by the ion density. Looking closer to the green area, showing the densities for a perturbed unit cell with defects, the boundedness of the vacancy density implies that a lower bound for the ion density exists. Thus, we limit the ion depletion by limiting the ion vacancy saturation. This effect can be incorporated into the model by assuming a statistical relation for the charge carrier density with the Fermi-Dirac integral of order -1 as the statistics function. This function is bounded by 0 and 1, and hence the vacancy density is bounded by 0 and the saturation constant called Na. To be consistent with semiconductor theory, we will call phi a quasi-Fermi potential instead of electrochemical potential. Now, with this knowledge, we can discuss proper current density descriptions. We know that the current density of a charge carrier is proportional to its thermodynamic driving force, which is in this case the negative gradient of quasi-Fermi potential. Also, for diffusion on a lattice, the generalized Einstein relation is true. Whether we assume now a constant diffusivity or a constant mobility results in two different flux expressions. For example, to be consistent with the electron and hole descriptions, we may assume a constant mobility resulting in nonlinear diffusion and this standard drift term. But on the other hand, we may assume a constant diffusivity, called in this case chemical diffusivity, which results in linear diffusion but a modified drift. To the best of our knowledge, there does not exist a work where the influence of both descriptions onto the charge transport model for perovskites was investigated. Thus, in the following, we will look closer to their numerical performances. For this, we use two open source software tools, Charge Transport and Ironmonger. While Charge Transport relies on finite volumes implemented in Julia, Ironmonger is based on a finite element method written in MATLAB. Within the steady state, it is quite easy to see that the models based on both current density expressions converge towards the same solution. The question is what happens when we are not in this regime, meaning simulating current voltage scaling protocols. For this, we introduce a scaling epsilon, which is given as the ratio between the average vacancy density incorporated into the model via the right-hand side of Poisson and the maximum vacancy density from the state equation. If epsilon tends to 0, meaning Na is much larger than Ca, then we recover the special case of neglecting the finite size of ions, resulting in a Boltzmann regime. If we choose Na to be equal to Ca, then we suppress ionic movement, reducing the model to the standard semiconductor device equations. In the following, we simulate a linear JV scan protocol for the most classical perovskite material, MAPI, sandwiched between transport layers with photogeneration happening from the right, or the illumination is coming from the right. Okay, so we do these simulations for variations of epsilon. We see here in the first row the evolution of the electric potential within the perovskite layer highlighted in red, whereas in the second row we have the evolution of the vacancy density. The first column corresponds to simulations of the model based on the nonlinear diffusion current density, and the right column corresponds to solutions of the model based on modified drift. So brighter color indicates here later time, and the colored lines correspond to solutions calculated with charge transport, and the black dotted lines to solutions calculated with Ironmonger. Not surprisingly, if you compare for this choice of epsilon the left and the right column, we see no difference in the solutions, since for this choice we are in a Boltzmann regime. Taking an epsilon equal to 1/2, we also do not observe differences between either nonlinear diffusion or a modified drift. Going further, For the modified drift case, we observe a slower evolution of the vacancy concentration, which also results in changes or in differences within the electric potential. Now, taking a more extreme value of epsilon strengthens this observation. Vacancy migration is almost suppressed here at the right interface for the modified drift, and this is directly linked to differences within the electric potential. Lastly, let us investigate the influence of these two current density descriptions onto the JV curves. We have here in the first row the JV curves for the case with illumination, and in the second for the case without. Brighter color indicates a larger choice of epsilon, and again, the colored lines correspond to solutions calculated with charge transport, and the black dotted ones to solutions calculated with ironmonger. A similar trend for all figures can be observed. The greater the epsilon, the more the curves are shifted to the left. For the modified drift current density approach, we see that the change in curves with respect to this difference between the smallest and the largest choice is greater than this change with respect to the difference for the nonlinear diffusion approach. Also, for the modified drift case, we see that a change in the JV is observed for a smaller choice of epsilon. For this, compare here these two curves where we see a difference, but both curves with the same choice of epsilon overlap for the nonlinear diffusion case. Now, bringing these simulated curves in a relation with measurement curves, one may argue that the difference between either nonlinear diffusion or modified drift may be minor, but for the sake of simplicity, we neglected other effects such as surface mechanisms. But this kind of effects may play a role and might affect the behavior of the model differently when assuming either nonlinear diffusion or a modified drift. Lastly, before ending this talk, let us shortly recap. We discussed how to include volume exclusion effects via the statistics function for ion migration. This results in two possible current density descriptions, which recover special cases of the charge transport model. When trying to identify regimes where these two descriptions differ, we observe that for larger choices of epsilon, the solutions based on the modified drift show a slower evolution of the ion profile. Lastly, we introduced two open source software tools which are based on different numerical techniques but show a good agreement. Of course, what we neglected here completely were other physical phenomena such as meaningful interface models. Thus, one continuation of this presentation may be to investigate the performance of these current density descriptions in a different setup, describing a more generalized drift diffusion model. But also for other device architectures based on different materials, it would be interesting to see a comparison between measurement and simulation. Also, what we did not discuss was the parameter sensitivity of other physical quantities such as band edge energies or permittivities. These quantities have an impact on the electric potential and thus on the vacancy densities. Both codes are available on GitHub and are hopefully explained in such a way that you can easily try them out. I thank you for your time and attention, and as always, if you have any questions, Please feel free to ask.